All right, welcome to part two of Regents Review. We're reviewing the January 2019 Regents. That's the January 23rd, 2019 Regents. We're going through, this is part two, so we're going through questions 9 through 24, right? 9 through 24. And you've kind of seen the level of questions that you've seen so far. So each day's lesson, you're going to find one easy question. Find one you think you can do. Remember, these are multiple choice. If you're not sure, at least take your best guess at the easiest one you think you can find, right? Then I want you to try to show someone else, at least tell them why you thought that was the right answer. So I want you to pick the easiest one. I want you to show someone else. It could be me, it could be a TA, it could be another student. Show someone else how you think that's right. Show someone else how to do that problem. And then part three is where you pick a question you think you can't possibly answer, and then find someone who can help you with that. Whether me, a TA, anyone in the room, that's all right. And another student, find someone who can help you with that problem. And then part four of each lesson of this week, we're going to go do a part two, a part three question. All right. So this video here is me going through questions 9 through 24. And so here's how you should do this. If you're stumped on a question, by all means, watch the video and get help on a question that you're stumped on. If it's one of those questions you think you can't possibly answer, and I'm busy helping another student, you can grab a Chromebook, watch this video, boop, get help on any question that you care to. What this video would not be very productive is if you were to just watch the video and just copy down the right answers and then not really engage your mind in how to think about these. You really want to try to think about why these are the right answers. Think about, did I know this? Is this review for me? Is this something new for me? You really want to just engage in the process and not just try to just get the right answers. Don't think of this as an exercise of getting the right answers. Think of this as a process of getting the right skills that you can take on the real Regents. All right? All right. So we're going to start with question number 9. Question number 9 says the graph of y equals 1/2 times x squared minus x minus 4 is shown below. That means is they're showing us this function. All right? They're showing us this function. The points A at -2, 0, -2, -2, 0. B, so this is A. -2, 0 means I go left 2, I go up and down 0, so that's A. B is at 0, -4. B is at 0, -4. B means I go left or 0 here means I go left to right 0. I don't go left to right at all. And I go down 4. 1, 2, 3, 4. That's this point right here. That's B. And C is 4, 0. 4, 0. I go to the right 4. 1, 2, 3, 4. And I go up and down 0, which means I got a point right there. So the points A, B, and C are on this graph. And we just identified all those 3 points. Now, hopefully, by this time, you know how to identify points on a graph. If you don't, you might want to try to practice, find some help, getting some extra practice, finding coordinate points on a graph. Very important skill. Can't do, it's just one of those basic things that they're just going to presume you know. So if you don't know it, get on that. All right. What's the question they're going to ask us? Which of these points can determine the zeros of the equation y equals 1/2 times x squared minus x minus 4? The zeros. They're asking us which one of these are the zeros. If you don't know what the zeros are, then this is a difficult question. But if you know what zeros mean, then this is a really easy question, isn't it? The zeros are where the function goes through the x-axis. Where y is 0, here's point C. Where y is 0, here's point A. Those are the zeros of this function. The x-intercept is going to be where x is 0 and y has a value. But right here, the point A has a -2 where y is 0, has a -2 value for x where y is 0. And point C here has a value of 4 where the y is 0, has a value of 4 for the x where the y is 0. So here are our 2 zeros. So we're looking for A only? No, not just A. B only? No, B is not a 0 at all. B is a y-intercept. A and C only? Yep, that's our answer. in A, B, and C. No, B is not a 0 of the function. It is a y-intercept. It's where x is 0. All right? So if you know what a 0 is, and you know your coordinate geometry points, some pretty basic stuff. I consider this to be an easy question. It does require that vocab, but I'm going to consider this an easy question, and I hope you do too. If it's not, you need to bump up those skills. Pardon me. All right. Well, I didn't expect that sneeze. Hope I was able to pause that in time to spare you the difficulty. Let me find our next page. I've been tearing these pages off because I don't like how it all sits when it's. I'm going to sneeze again. Uh-oh. Pardon me, this is my study, and I've got a nice, beautiful wall of windows over here, and I've got them all open, enjoying our nice Saturday weather we have right now, and perhaps my allergies are acting up. Okay. Given the parent function, the f of x equals x to the third, the function g of x equals the expression x minus 1 to the third minus 2, the result is the result of a shift of the f of x. Okay. So they're saying we're going from this function here to the f of x, and we're moving towards this function over here, the g of x. And notice what's the same here and what's different. What's the same here? Well, what's the same on this function? What's the same as on this function is that we have x to the third power here. So you can see that. And we have x, eventually we'll go to the third power on this expression too. So this is going to be x to the third. This is going to be a cubic function. You have not, unless you're in my Algebra 2 class, you're not familiar with cubic functions. That's okay. We did spend a whole unit on transformations of functions. We learned about what happens when we add to the end of a function. It goes up and down. We learned that when we add or subtract directly from the x value, it makes our function go left or right on the graph. All right. So notice how x minus 1 cubed is really going to be, x minus 1 times x minus 1 times x minus 1. And when I distribute this to this to this, I'm going to end up with an expression that has x to the third power that goes on. It's going to have a lot more than that, right? Because then I'm going to have, x x to the x to the negative first, and this is going to get to be a big giant function. But let's go back. The f of x is x to the third. That's our parent function. Now what we've done is we subtracted 2. We subtracted 2 to the end of the function. That's going to make our function go down 2 units. And we've subtracted 1 directly from the x. That is going to make our function go to the right 1 unit. Okay? It's kind of weird how that works. When you subtract over here on a function, it makes the function go down. When you add over to the end of the function, it makes the function go up. When you subtract from the x, it makes it go to the right. Actually, I'm not going to point anymore left or right because my right and your right may not be the difference. When I'm going to the right, I'm pointing to the right now. If this isn't the right for you, then you got to. I don't know how the camera's going to work. Sometimes the camera reverses left and right, so I apologize if I just confused you. But the x minus 1 is going to make our function go to the right, and the x plus 1, if you were to add to the right directly to the x, it would go to the left. All right. So we're looking for one that tells us that it goes down 2, it goes to the right 1. So unit goes to the right 1, goes 2 down. That's our choice. Golly, I kind of want to say this is a medium to easy problem. It takes some thinking. Why it's not just easy is because it's got a cubic function, and you're not used to seeing those. But if you remember our function transformation rules, how to make functions move all around, we learned that if the bigger the number we add to the linear function, the higher its y-intercept is, right? Right? The number we add to the end of a linear function is where its y-intercept is. And we saw that with quadratics too. We could raise a quadratic up or down from where the parent function is by adding or subtracting to the end of the function. And then we saw how by subtracting directly from the x function, we could make it do all sorts of good stuff too. Left to right. So I'm considering this medium to easy myself. Let's take a look at this next one. It says if c equals 2 times a to the second power. Sorry, I gotta 2 times a to the second power minus 5, and d equals 3 minus a, then c minus 2d equals, okay. Pause the video here. See if you can think about this and make some sense of this. Pause it here, take a look. All right, hopefully you've thought about this. Hopefully the first thing that came to my mind at least, hopefully the first thing that came to yours, is that it's going to be hard to solve this problem unless I know what 2d is. 2d is 2 times d. If d equals 3 minus a, then 2 times d, or 2d, actually I probably shouldn't have, 2 times d is going to be equal to 2 times 3 minus a. And how would I do this, right? How would I do this? I'm going to distribute that 2 across the parentheses here, and then across the parentheses there. So I'm going to get 2d equals 2 times 3 is 6. 2 times negative a is negative 2a. All right, now I can rewrite this is now my 2d. I'm going to take the c function. I'm going to subtract it by my new one. So I have 2a squared minus 5. Ooh, and this is where I think this goes from an easy problem to at least a medium. Is minus 2a. Notice that I have to put this whole expression, 6 minus 2a, inside of parentheses, right? Because I'm subtracting the whole thing, not just the 6. I can't just say minus 6 minus 2a. No, I'm subtracting 6 minus 2a. Well, subtracting an expression in a parentheses, I'm going to need to pretend like there's a negative 1 out in here. I'm going to need to distribute that negative 1 to the 6. Distribute the negative 1 to the negative 2a, and I'm going to get negative 6. Because negative 1 times 6 is negative 6. A negative times a negative here is going to be a positive. 1 times 2a, positive 2a. And then I treat the rest of this like an addition problem. Whew, it's so long that I'm not going to be able to write it over here. I'm going to write it underneath it, and I'm going into my problem 12 space. That's okay. No big deal. I'm looking for my like terms. Well, my only 2 like terms are these 2, so I can combine those eventually. I'm going to rewrite this as 2a to the second. There's no more a to the second terms, so it's all by itself. Then I'm going to look for the 2a term. There's that a term there. 2 times a. Is there anything else times a? Nope. So 2a. And then negative 5 plus negative 6 is negative 11. Do I have a choice that looks like this? Oh, yes, I do. Boop. There we go. Choice number 3 there, right? Yeah, this is definitely medium difficulty because not only do you have to multiply an expression 3 minus a, distribute that 2 across the parentheses to find out what 2d is. Then you need to subtract the whole expression of 2d, which means knowing to distribute a negative 1 across the parentheses. So all said and told, I'm going to call this a medium one. But it's just distribution when it comes down to it. It's just an equation set up with some distribution. So it's a medium difficulty. There's at least 2 steps, if not 3, to get in there. I had to write quite a bit to get there. But just, easy does it. You'll get there. You'll get there too. All right, if you stick with it. Just got to stick with it. Let's go to question 12. Question 12. Mark bought a new laptop for $1,250. Woo. He kept track of the value of the laptop over the next 3 years, as shown in the table below. Okay, 1 year after he purchased his laptop, the value of the laptop was only $1,000. So if he was going to sell it after 1 year, he could only get $1,000 for it. After 2 years, if he wanted to sell it, he could resell it for $800. After 3 years, if he wanted to sell his laptop that he originally spent $1,250 for, he could only sell it for $640 after just 3 years. So what function can be used to determine the value of the laptop X years after purchase? So this is kind of a thinking question. You're going to have to look at how these numbers are changing and find a relationship, find a common relationship. If it's a linear function, then you're thinking about something that's decreasing by the same amount for every year. If it's an exponential function, you're looking for it to have a decreasing by a multiplier, decreasing by dividing it by a certain amount each time. So pause this here, see what you can do with it. All right, you're unpausing because you tried something, right? You're not just waiting for the right answers. You're here to learn and review. Hopefully that's your learning target this week. All right, your learning target is that you can review and practice your Algebra 1 skills. You should be able to say, I can review and practice my Algebra 1 skills by the end of these lessons, each one of them. All right, hit that learning target. All right, notice here, so I suggested to you that maybe you want to look for a linear function and then throw that out. Actually, they're not even giving you a linear function here. All the options are linear functions. All the options are linear functions. And I can immediately, well, looking at my options, this became a really easy problem. So, sorry, didn't mean to. After I looked at the options, it immediately became clear to me. I started eliminating things. So, first of all, I need to figure out where this function is starting, right? Where is this function starting? So one of the things you could do is you could put each one of these functions in your graphing calculator, because they're giving you 4 functions. You could put each one, you could say 1250 times 1.2 to the x power, and you could go to your table, and you could ask yourself, does my table look like the table on, my table here look like the table that's on, that they give me? If it does, then I've got the function. If it doesn't, then I don't have the function. And indeed, at 0, I'm at 1250. At 1, I'm at 1500. Oh my gosh! When I have when I have an exponential function that's greater than 1, it's going to go up, right? Because I'm keeping the original value. That's the multiplying by 1, and then I'm increasing by whatever it's added to 1. So in this case, it's 0.2. I'm increasing this function here has me increasing the value by 20% each time. Nope, can't be that guy. We can cross that option off. Let's look at, let's cross this one off too, because this also is being multiplied by 1.2. This is a function that is increasing. So we can already eliminate those ones. I'm going to put 1,000 times 0.8 to the x power. And actually, let me slow down. Let me show you how I did that, just so you know how to do this, all right? Clearing this. 1,000, 1,000, right? 1,000 times parentheses. See my parentheses right there? Make sure you can see everything on my calculator here. Parentheses, 0.8, parentheses right here, above the 9, closing the parentheses. And I'm going to raise it to the x power. I'm going to do that by pressing the caret button, boop, and then I'm going to press the x button, boop. All right, I'm done. That is the function. I'm going to go to my table now. I go to my table by pressing the blue second button, and pressing the graph button, which says table in blue. And there's my table. If I went too fast there, if you didn't catch that, go in reverse. That's the great thing about video, is you can keep watching these over and over if you need to. All right. On this graph, I'm close. I'm close. Look at this. It goes from 1,000 to 800 to 640, but the problem is it's at 1, it's at 800. Whereas on my table on my Regents, it says at 2, I'm 800. At 2, I'm at 640. Well, the table I have here says I'm at 640 on my other one. So I'm guessing by process of elimination, we can assume that it's this 4th option here. And let's just confirm it with our calculators. I went back to y equals. I changed it to the other number to 1,250. And indeed, now we have a function whose tables match. We have used our calculator to discover the function whose tables match. The other way to do this is to say, okay, the function has to start at 1,250. So the first number I have in front has to be 1,250, which means I can eliminate these two right off the bat. Function starts, the laptop was purchased at 1,250. That's what the function starts. That's the number I should have out in front of an exponential function. The second number should be the multiplier. I should be, as I'm looking at this, I would start saying, oh, well, 800 divided by 1,000 is 0.8. 640 divided by 800 is 0.8, which means I'm multiplying each number by 0.8. Watch this. So make sure you can see what I'm doing. 1,000 times 0.8 is 800. We went from 1,000 to 800. 800 times 0.8 is 640. We went from 800 on our table here to 640. Do you see how this function works? For every year that progresses, this function progresses, this amount goes down by 20%, or being multiplied by 0.8 for every year to the power of every year. All right? I'm going to say that one is easy to medium. I mean, especially if you know anything about the basics about exponential functions, if you know that first number is the starting point, if you know the second number, the b value is the multiplier, and that it's to the x power. I think you could look at this and just with a little bit of figuring, using your calculator or doing it on paper like I might do, you'll be fine. You'll be fine on this. So I think this is in between a medium to an easy. It's only a little bit hard because you do have to remember about exponential functions. We did spend quite a lot of time in that on quarter 2 on exponential functions, more than usually is spent on a Regents Algebra 1 review. But exponential functions are so important, we decided to do them. So let's do number 13 here. Number 13. The height of a ball, Doreen tossed into the air, can be modeled by the function the h of x equals negative 4.9 x squared plus 6x plus 5, where x is the time elapsed in seconds and the h of x is the height in meters. The number 5 in this function represents. All right. So this is just a basic, do you know the pieces of a quadratic function? Do you know the pieces of a quadratic function? All right. One thing you should know about quadratic function is their general shape. You should have a U shape, either an upside down U or a right side up U. So either upside down like a frowny face or a right side up U like a smiley face. Quadratic functions should have a U shape. And you'll know that they're quadratic when it has x to the second power. An x to the second power, all right? Well, so there's two things going on. First, we have, whenever you think about a quadratic function, you want to think about two forces that are kind of acting against each other. So like the classic example is tossing a ball up in the air, right? That's the classic quadratic function modeling. I toss a ball in the air, okay? There's the force that I'm applying to push it up. And at first, that force that I use to push it up is strong enough to make the ball go up, 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 up. But what happens? It starts slowing down, right? Because eventually gravity is also, well, not eventually, the moment it leaves actually gravity is there as a constant. The gravity is always pulling down the ball. I push it up. The moment it's constantly being pulled down by gravity, but I push it up. It's going up, but it's slowing down because now the forces pushing it up are wearing off. That energy is being converted into potential energy, kinetic into potential for those science people out there, and then it starts going down. Gravity eventually wins, right? The energy of gravity eventually overpowers the amount of energy I meant to push it up, unless I was able to make it escape the gravity well of the Earth, right? So, not being Superman, that ball's coming down. So, This is the force of gravity in an exponential function. That's the force that eventually wins. That's the force that is squared. Okay? So the force that's eventually going to win this thing, it's going to make that thing make the tails of your quadratic function shoot up into the sky or shoot down into the negatives. If you think of a normal quadratic, it goes up, 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 and then comes back down. Well, the force that's pushing down constantly, that's going to win the battle, that's your gravity, right? And sometimes you can have forces that are going to make things go into the ceiling. You're going to have a U-shape, smiley face, U-shape the other way. But this one, we're going to have a frowny face, U-shape, because it's a negative out in front. Remember we learned negative, frowny. Positive quadratic, smiley. Smiley for positive quadratics, frowny for negative quadratics, okay? This is the force that's eventually going to win. This is the force that's pushing against the force that's eventually going to win. In this case, 6x is the energy she puts into it to push it up into the air. It's enough at first to make the ball go up, but eventually gravity wins and pulls it back down. This plus 5, that's your constant. That's the height you initially threw it at. So when she throws it into the air, the moment the ball leaves her hand, that's the 5. It left her hand at 5 feet above the ground because the function is a model of the height of the ball over time, right? Over time. So the ball's going up, 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 and then the ball starts coming back down, 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 down. It started at 5 when it left her hand, and we can find out when it will hit her hand again, or we can actually, if she removes her hand, we can find out when it hits the ground and stops. So that 5, what does 5 mean? It's the initial height of the ball. Number 1. I kind of think this was a pretty easy question. But maybe that's because I'm familiar with quadratics and I know what the pieces mean. If you didn't know what the pieces of quadratics meant, and how to look at a quadratic function, you need to review your quadratics. All right. This is kind of that we did lots and lots of work on quadratics and what they mean and function transformations and this kind of stuff. We would add to the initial height and show how that changed the graph. Review those things. Ask for help. If this is a weak spot for you, identify that for yourself and get some help. All right. Number 14. Here we go. The function f of x is equal to 2 times x squared plus 6x minus 12. This has a domain consisting of the integers from -2 to 1. Pardon me. Inclusive. Which set represents the corresponding range values for the f of x? Okay, so you have to know some vocab terms here. You have to know what domain is. You have to know hopefully you know what integers are. We'll talk about those. And range values, okay? Domain, my house is my domain. So think of the 4 walls of your house. My house is my domain. It's an expression some people sometimes use. If your house is your domain, then the 4 walls of your house from side to side, that's your domain. So on a graph, our domain is our x values from side to side. They're the walls of our house. The domain is how far the function goes to the all the way that way and all the way that way from side to side. The range, think of a mountain range, all right? Mountains go up and down. A mountain range goes up and down. So when you think range, you're thinking the values that go up and down, the y values. So what this is asking is, what it's saying is that the domain of this function goes from -2 to 1. It's saying then, if that's the domain, if it goes from -2 to 1, what is the range? Well, I'm going to break out my handy-dandy calculator in a circumstance like this. What I could do, I could plug -2 into this function, find the value of y. Plug -1 into the function, find the value of y. I could go that route and make this happen. But I find it would be much easier for me. Oh, let me show you what I'm pressing. This is Algebra 1 review. We need to review what buttons to press. So I have C 2x squared. 2x squared. And then it's plus 6x minus 12. Okay? I'm going to graph this function just to show you what it looks like. There it is. It's going down, 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 and then it's going back up. That's fine. I'm going to go to the table. That's what I'm really interested in. Almost always, we're more interested in the table than anything else, to be honest with you. I'm going to go to -2. Oh, it already is at -2. Oh, how convenient. At -2, I'm at -16. All right. So I need to get rid of anything that doesn't have 16 in it. So this goes away. This goes away. These sets of data here don't have -16 as one of my values. And yet clearly, if my domain is from -2 to 1, and I have at -2, when my x is -2, my y is -16 as my table, my calculator says, I get to eliminate any set that doesn't have -16 in it. I know -16 has to belong to this set. I'm going to look at, let's see, -1, also -16. Okay, all right. 0, -12. Well, I can now eliminate this choice number 4 here, and then I'm going to go to 1 just in case. I should see a -4. So you see this on my calculator, how I've got -16, 12, and -4 as the values, the y values for that domain. Well, this number 2 is our choice. These are our range values for this function. I got to give this more of an easy one. You know, literally you can put that in your calculator. You can go to your table and you can find the answer pretty quick. You know, the domain is -2, 1, 0, 1. So really there's only 4 numbers to plug into this thing. I could literally plug -2 into this function manually without ever going to the table. It's more work. Let me show you what that would look like if I don't want to plug each one of the. I'm not going to plug them all in. That's too much. But 2 times -2 is my first integer value to the power of x. No. To the power of 2. 6 times -2. Remember, I'm plugging -2 into wherever I see x here. And then -12. I could plug. Uh-oh. Mr. Solt has clearly missed a parentheses where a parentheses was needed. Oh, because I'm plugging -2. What am I doing here? Look at me making all those mistakes. Well, maybe that'll make you feel better so that you don't need to feel bad you make mistakes, because I make them too. And clearly I'm doing something wrong yet again. Had to pause there and say, okay, what mistake am I making? Didn't want to waste your time. So I realized when I first put it in, I got -108. That didn't work. Something's wrong here. And then I got -28. I'm like, what am I doing wrong? When things don't make sense, when they don't add up, persevere, stick with it. You know, think about it. Go back and did I make a mistake somewhere? Where is there an error here? So here was my error, is I didn't have this -2 to the second power, as my function clearly has to have. I've got x to the second power, which means I need my -2 to be to the second power. When I do that, I get -16, just like my table showed me. Everything's hunky-dory. So yeah, I would, you could plug all those the 4 integers in for the range. Sorry, for the domain, and you'd get your range values, and everything would be good. Or you can use your calculator and kind of figure it all out with the calculator. I'm going to give that one an easy one. Which equation has the same solution as x squared plus 8x minus 33 equals 0? Well, my first instinct was to jump to my calculator and plug this function in. But as I saw my choices, I realized, oh, I have to manipulate this a little bit. I'm going to have to manipulate this one. And you know what? I don't think I taught you completing the square in our Algebra 1 review. So you have not really had any practice with this unless you learned this from another Algebra 1 teacher. All right, there's this thing called completing the square. All right. So I just rewrote the equation to show you my first step. My first step is completing the square is when you take the constant off the back of the quadratic function and you move it to the other side of the equation. And then what you do is you insert a number to the quadratic that will then complete that square, that will make that side a perfect square. And then that allows you to square root both sides of the equation. which can solve x. Under certain circumstances, this is a great way to go. But I've already taught you how to do it with factoring, and I taught you how to figure it out with your calculator through the table and the graph. We did 1 day of the quadratic formula, which you all hated because it was too much. So there are other ways. There are lots of ways to get the job done. We're going to do it completing the square right now. All right. I'm going to add 33. I'm going to add 33. And yeah, sometimes in math you have to persevere, and sometimes there's a lot of work to find one answer. But sometimes finding one answer can be worth it. All right, so you see what I did here? I added 33 to both sides of an equation. We have lots of practice doing stuff like this. It's that addition property of equality. We can add the same amount to both sides of an equal sign, both sides of an equation, and it's fine. The equation is still going to be equal. Notice I added a box here. I added a box. And I'm going to add a box to both sides, because now I need to complete this square. And there's really not much to do other than to memorize this. You need to memorize a formula. B divided by 2 squared is what you put in that box. Honestly, I always get this messed up myself. I sometimes think it's something else when it's not. I'm not going to tell you what I always think it is because I don't want you to get that stuck in your head. But b divided by 2 squared. All right? So here's my b term. My b term is 8. It's this middle term that's not x squared, right? It's that middle term in between. So in this case, my b term is 8. 8 divided by 2 is 4. 4 squared is 16. So 16 is the number I got to add to both sides of my equation. So everything so far is actually properties of equations you've already seen. I'm just adding 33 to both sides of my equation, and now I'm adding 16 to both sides of my equation. You've done adding to both sides of an equation before. That shouldn't be hard. The difficulty is you didn't know that you could not only move something to one side of an equation because to get rid of it on that side of the equation, but you can add any old number for any old reason at all to an equation, and it still works. So now, though, I've set myself up for some good magic stuff to happen, all right? It may not occur to you, but I can now factor this problem very easy. This is very factorable. X plus 4 squared. I made it be easy, all right? I made it be easy because I know that 4 times 4 is 16, right? 4 times 4 is 16. 4 plus 4 is 8. When I factor this out, if I was to factor x plus 4 times x plus 4, I would do x times x, which is x squared. I would do x times 4, which is plus 4x. I would do 4 times x, which is plus 4x. And I would do 4 times 4, which is 16. When I added these two 4's together, I would get x squared plus 8x plus 16, just like I have here. X squared plus 8x plus 16. So this x squared plus 8x plus 16 is the same thing as x plus 4 squared. I FOILed that out to show you. What's 33 plus 16? Well, that just so happens to be 49. If that didn't jump out of your head, that's okay. That's what those calculating tools are for. You just plug those numbers in there, you're good. All right. Now, this is where the magic of completing the square is. I square root both sides, right? It doesn't get any easier than square rooting something that's squared. That just becomes, here, I'm going to square root. There's my square root symbol. Square root. This becomes x plus 4. You know what the square root of 49 is? 7? 7, right? Plug that. If you don't know that, you plug it in your calculator. It's okay if you don't know it. The square root of 49, your calculator can help you out with that. 7, right? There's the square root button. It's right under the x. It's in blue. Oh, sorry. The square root button is in blue. You press the X. You press the blue button first, the blue second button. You press that x squared button, which is really your square root button, and you put in a perfect square in there. Press enter. It gives you that square root. All right, it's 7. X plus 4 equals 7. Well, now this should be an easy equation at this point. Minus 4 on both sides. Minus 4 on both sides. Minus 4. I get an answer that's x is equal to 7. I'm sorry. plus or minus 7 minus 4. Plus or minus 7 minus 4. Mr. Solt, why is it plus or minus 7? Well, because I square rooted 49, and negative 7 times negative 7 gives me 49, but also positive 7 times positive 7 gives me 49, so it's plus or minus. But I didn't need to do all that. Actually, once I got this far, I could have stopped with this problem. I just wanted to show you how to complete the square, since we were almost done with that. X plus 4 squared equals 49. X plus 4 squared equals 49 is the exact same equation as our original equation here, x squared 8 minus 32. So I'm trying to think of a good way for you to solve this on your calculator. I thought of a way. Let's see if we can do this an easier way, because you're probably not going to remember how to do completing the square, and that's okay. If you didn't like the quadratic function, you're not going to like completing the square. You could. It's going to take you time, though. It's going to take you time to do this. You're going to have to put all 5 of these equations in your calculator. Now notice that when I put this in my calculator, I did minus 49. Why did I do that? Because if this equation over here is equal to 0, I want my next one to be equal to 0 as well. Which means if I want this function here to be equal to 0, I have to minus 49. I have to move that 49 to the other side to get this equation equal to 0. And then I'm going to go to, I can go to my graph and kind of get a picture of where these two functions are going to be the same. But a table is even better. And notice that on my table, all my values are the same. Where x is negative 2, my y values are negative 45, negative 45. Where x is 4, my y values are 15, y value is 15. When x is 8, y value is 95, y value is 95. That means these functions lay on top of each other. These are the exact same function. You could find that out by plugging it in your calculator and seeing which ones are exactly the same. That's one way to solve that with your calculator. I'm going to give this a medium difficulty. I don't feel that that's super difficult, especially given the fact that you could use your calculator to kind of find this out. A lot of button pushing, a little bit of time, but you could do that. You could do that. I don't think I have many students who I wouldn't have confidence in being able to plug all 5 of those equations in their calculators and finding which one matches. I know some of you might not want to do it. That's another thing. The table below shows the weights of Liam's pumpkins. The L of W. So Liam's function, his weight of his pumpkin is the L of W, and Patricia's pumpkin, the P of W, over a 4-week period where W represents the number of weeks. So W is number of weeks, and this is the Liam's function. This is Patricia's function. Liam's pumpkin grows at a constant rate. Ooh, keyword there, constant rate. Constant rate. Hopefully you are thinking what I'm thinking. I'm thinking Liam, if Liam's pumpkin is growing at a constant rate, the function of Liam's pumpkin is a linear function. It's a straight line going up. It's at a constant rate because lines have constant rates of change, okay? Patricia's pumpkin grows at a weekly rate of approximately 52%. Ooh, 52% increases every week? That's an exponential function. Well, one thing we know is that exponential functions are eventually going to exceed linear functions if they're both increasing, if we're thinking about infinity. But under the short term, we need to actually test this out. So let me put these functions in here. Oh, they didn't give me the function rules, did they? Well, the difficulty of this problem just went up just a little bit. So let me do the L of W. There's my L of W. What do I need for a linear function? I need y equals mx plus b. All right, where m is my slope. So I'm going to do my slope first. I'm going to calculate the slope by 5.5. 5.5 minus 2.4. That's 3.1. 8.6 minus 5.5 is 3.1. Oh, that was interesting. 11.7 minus 8.6. Oh, it's 3.1. This minus this is 3.1. Oh, let me make sure this is even so you can see that. This minus this is 3.1. This minus this is 3.1. And this minus this is 3.1. Liam's pumpkin is growing at a rate of 3.1 every week. So I could actually start to make, instead of writing out my thing, I could, when do they want me to find out? I have to read the statement, I have to read the question. Assume the pumpkins continue to growing at these rates through week 13. They want me to go all the way to week 13. Ugh. When comparing the weights of both Liam and Patricia's pumpkins in week 10 and week 13, which statement is true? So I need to find out both of these pumpkins at week 10 and 13. At week 10 and 13. I want to create a formula. I want to create a formula myself. So I said that these are increasing by 3.1 each time, x, and it starts at, all right. For me, it's easier to just say, I want to find the function rule, and I know it's increasing by 3.1 for every x, and then I'm going to take 3.1 and I'm going to subtract it to to week 5, keep going down until I get to week 0 to find the y-intercept. It's going to be negative 16.2. I can show you how I did that. So what I did was I said, okay, at week 6 I had 2.4, right? At week 6 I had 2.4. So I put 2.4 in my calculator, and I said 2.4 subtract 3.1. That's how much it's increasing by. I want to subtract 3.1 because I want to find out what it would be mathematically at week 0. Now, in reality, we're not going to get into negative weights, right? That doesn't make sense, but mathematically it makes sense. 2.4 minus 3.1 times 6, because I go down to week 5, week 4, week 3, week 2, week 1, week 0. I need to go back 6. So I need to subtract 3.1 for 6 times over. That's 16.2. That tells me that the y-intercept for this function is 16.2, which means I can put that in my y equals. And I'm going to get a table. And I could immediately go look and say, hey, at week 10, this, let me write this out so you can see it. The L of 10 is equal to 14.8, and the L of 13 is 24.1. Whoops, 24.1. 24.1. Yeah. Let me show the calculator on that. So do you see that? There's my y equals. There's I put the equation in that I found in my y equals, and I went to my table, and I found what 10 was, and I found what it was at 13. All right? Now, maybe you don't want to do that. Maybe you don't want to do that, and that's okay. I can understand how what I did was a couple different steps, and maybe that's too many steps for you. All right, let me meet you where you are. Let's talk about week 9. We know this is increasing by 3.1. That's unavoidable. You got to find what it's increasing by. 11.7 increasing by 3.1. This is what it's at week 10. Oh, that's what we found over here. At week 11, it's going to increase by another 3.1. So you add 3.1 again. Add 3.1. This is week 11. Add 3.1 again. That's week 12. Add 3.1 again. That's week 13. So you can solve that on your calculator, easy peasy lemon squeezy, just by adding 3.1 and just remembering what week you're on and writing that down. Me, I want to find the function rule. That's just me. All right, so now I need to find the exponential function rule for Patricia here, and I remember that exponential functions are y equals a times b to the x power. So I'm going to have p of w is going to equal the starting point of where it started. So I need to find out where this started. 3.8 divided by 2.5. And then I need to, I'm increasing by 52%, just like was said. So if I start at 2.5 and I subtract 1 minus 0.52, and then times 6. Nope. One moment. Sorry. All right. So as I was playing around with the numbers here, I did come up with the formula. Honestly, it took me 2 or 3 minutes playing around with the numbers of saying, well, what's this? What's that? Eventually what I did was I took the original 2.5, and I divided it by the 1.52. I need to reverse the increase of increasing by 52% a couple times. I need to reverse it by 6 times because I'm going back 6 weeks. So I'm increasing it. I'm dividing it by 6 times. In fact, what I could do is point and then divide it by 1.52 to the power of 6. And I come up with this number here. This magic number is the one where it began. So I can use this magic number, my y equals. I'm going to use this magic number here, which is going to be 2.5 times, divided by 1.52 to the 6th power of 6. I want to go down. There we go. Close parentheses times 1.52 to the power of x. All right. Whew, that's a lot of work, and I'm kind of thinking that most of you don't want to do that much work on these problems. So let me try to show you a different way, and it's not that bad. It's not that bad. Let me just, since I did all this work, I'm going to write down what I got. What I got was that the P of W, the P of 10. P of 10, so that W didn't look too far off from a 10. The P of 10 got me 13.345, and then at week 13, the P of 13 gave me 46.865. Now let's go back and see how we could do this a little bit easier. All right, let's get rid of the funky math. How do I break it down? Well, you take 3.8, and then you divide it by 2.5. You're looking for, okay, what's the relationship between these? I take 8.8, the biggest number, divided by the number next to it, 5.8. I'm getting something close to 1.52 each time. Let me try this. 5.8 divided by 3.8. Oh, another 1.52. So actually, this requires some interpretation. You're going to have to realize this is going up by 1.52 each time. Now, the reason why it's not coming out to be exactly 1.52 is there's some rounding going on here. Mathematicians, we don't like rounding too often. But anyway, so now we know, and it told us it's increasing by, 52%. So let me take my 8.8. That's what it was at week 9. I'm going to times it by 1.52. Why 1.52? Because I want it to increase by itself plus 52%. So at week 10, I'm at 13.376. And it's because I'm rounding. So my answer here wasn't exact to what I have over here, but that's because there's some rounding. Some rounding has been happening. I'm going to times this by 1.52 again to get week 11, times 1.52 to get week 12, times 1.52 to get week 13. And at week 13, I have 46.97, which is not as exact as what I found on my table, but my table was much more exact because I found the exact, origin. So some rounding is happening. So that's why our numbers aren't completely matching, but notice how close they are to each other, right? 46.8, 46.9. We're really in the same ballpark. We're talking about the same function. And all of that, let's go to the question and find out what's happening, what's true about week 10 and week 13. Liam's pumpkin will weigh more in week 10 and week 13. Liam's pumpkin is going to weigh more in week 10 than Patricia's, but Patricia's pumpkin, as we can see, is going to weigh 46 pounds on week 13. Liam's is only going to weigh 24 pounds. So number one, not true. Patricia's pumpkin will weigh more in week 10. That's not true. And week 13, not true. Liam's pumpkin will weigh more in week 10. That's true. His is 14, hers is 13. And Patricia's pumpkin will weigh more in 13. That's true. And then they're going to reverse that, right? Patricia's pumpkin will weigh more in week 10, which is not true. And Liam's pumpkin will weigh more in week 13, which is not true. Number 3 is our option. You know, I'm going to give that a medium to hard. A medium to hard. All said and told, it's not that bad, but you have to either set up a linear function or find rates of change for a linear function and then identify it as a linear function. Then you need to extrapolate that to figure out what it's going to be at week 10 and week 13, which requires a lot of buttons pushing. Then you've got to figure out what an exponential function, how to get an exponential function to increase by 52%. Remember, you need to multiply by 1.52, boop, 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 to get week 10 and week 13. There's some steps to that. I got to be honest. I'm going to go with a medium to hard one for that question. All right, we're done with 16 here. Let's go on to 17. Let's go on to 17. Oh, wait. Should we do? Yes, we should do 17. 17 is going to be our last one for this video. All right, 17 is our last one for this video. So 17. 17. The function f of x is graphed below. The f of x? Okay. Can you see? Can you take a look at that right there? This is a v shape. Hopefully you know this is an absolute value function. Don't need to know this for the problem, but I want you to know that v-shaped functions are absolute value functions. And let's see. I see a dot right here. I see the function's going down. I see it's going up, and I see an arrow right there. The question is, the domain of the function above is it all positive real numbers? Is it all positive integers? Is it x is greater than or equal to 0? Or is the domain here x is greater than or equal to -1? Well, to solve this question, you have to know what this dot means. You have to know what this arrow means. You have to know what a domain means. And you have to know what some inequality notation means. Well, this dot right here means this function starts at that point. That's a dot. This function starts at that point. That arrow means this function continues on towards infinity in exactly that direction. All right? It keeps going on like this forever. So, when it asks me about the domain, I talk about this. My house is my domain. All right? It's the four walls of my house. It's side to side. It's saying the x values. The x values of this function. Notice the x values of this function start at -1. Do they go on to -2? No, they do not. That dot says this function starts here, and that's exactly where it starts, right? So my x values start at -1. -2 does not belong to the domain of this function. So all positive real numbers doesn't quite work because I've got a negative in here. All positive integers doesn't quite work because I've got a negative in here. I have a domain that -1 belongs in this domain. I see it goes on to, the domain continues down to 0, continues on to 1, continues to 1.5, continues to 2, 3, 4, and then it's going to go towards infinity in a positive direction. So my domain for this function is going to be x is greater than or equal to -1. Starts at -1, goes infinitely in the other direction. So all positive real numbers can't be included because I have a -1. It's part of my domain. All positive integers can't be included. No, it starts before 0. X is greater than or equal to 1. I got to kind of give that an easy one. There's some vocab in there you have to know. There's some notation you have to know. But I'm hoping you know what a dot means. That means where the function starts. The arrows mean that's where the function goes on forever. Hoping that works for you. So these looks like it takes me about an hour to explain about 8 questions. That's okay. The video is going to be an hour long. All right. Have a good day. Hope you're learning good stuff. Hope this is of value to you to go over this Regents. Again, I want you to see that these Regents aren't that scary. That you can do it. You got to persevere. You got to push through. You got to look for your mistakes. You got to correct. You got to know the vocab. You got to keep your fundamental skills of algebra keen, sharp, tight, and you're gonna do all right. You're gonna get through this. All right. I know I make it look easy and everything, but you can do it too. All right? We're going to do it together. Until next time.